Okay, so now it's time to introduce a new topic, which is elasticity. Um, and we have covered all sorts of topics from very different disciplines, but all of them are actually the basics from many different areas of physics. And so this course is sort of designed to cover all the basics from many different areas. So talking about elasticity, um, all this understanding of elasticity and things related to that is actually used in mechanical engineering. So let's go through some of the basic stuff. So beginning with, let's say if we have a wire and this wire has length L, and you apply a force F to it. So in our real life experience, we know that there will be a change in length of the wire. That means there will be an increase in length of this wire, and let's say this length is equal to delta L. Okay, now let's see on what factors this delta L depends. For sure, if you increase the force F, there will be an increase in length, so delta L is proportional to F, which means increasing F increases delta L. Also, we know if the wire is longer in length, then there will be more stretch in the wire. So with a longer L, there is a bigger delta L, which means a bigger L gives a bigger delta L. Just to clarify the point, this wire will stretch less compared to that wire with the same force. So this wire is going to stretch more or have a bigger delta L than this wire for the same force F. This is also true. What else? There is one more factor, which is that delta L is proportional to 1 over area, which means that if the wire have the same length, and if you apply the same force on the wire, the one which has a lesser area, which means let's say if A1 is less than A2, then delta L1 will be more than delta L2, which means a thinner wire will stretch more than a thicker wire. So that also makes sense. And all of these can be combined to write in a formula which is given as that delta L will be equal to F over A Y times L. This is the formula. So as you can see, delta L depends directly on F, delta L depends directly on L, and delta L depends indirectly on A. And this Y is the proportionality constant that is connecting these variables, and this Y is called the Young's modulus. And the Young's modulus just depends on the type of material which is being used here in the wire. Is it iron or steel or what, or copper? So Y depends only on the metal or whatever substance which is being used, and this is the governing formula. You might have actually also noticed that you can rewrite this formula as delta L equals YL over A F. And if you recall from Hooke's law, you see this whole formula looks very close to Hooke's law, which said, or in fact you can rearrange this to write F equals A over YL delta L, and recalling Hooke's law, which said F equals K delta X, change in length. So for this particular wire with these parameters, that is Y, A and L,
for a wire with given A, given L, and given Y, we know K is going to be A divided by YL. Okay, so this is all about Young's modulus, and this is the deformation or elongation in the direction. Well, this is a normal deformation, you can say normal elongation, because the force that is causing the elongation is normal here. So is normal to the surface. So this is the surface, and the force is normal to it. So it's a normal. If you see a cross section of the wire, this is how force is acting. So that's why it's called it's a sort of normal elongation, and the term used is Young's modulus. Also, there is one more thing in which we do not have normal elongation, like for example this case. Let's say we have a metal block, something like this, and we apply a force on the surface of on the top surface of the block. So what we'll observe is that this is what will happen. If this is how we start, then the new surface will start looking like something like this. It will deform like that, and this deformation is called shear, shearing deformation, or shearing deformation. I am using my own vocabulary, but it's because of the shearing force. The force is shearing. I forgot to mention in the last example that you can rearrange the formula to look like this. This is Young's modulus, and F over A is called the stress, and delta L over L is called strain. These are the names of the variable, and we have sort of always assumed that delta L is very much less than L. So even increasing or the increase in length sort of keeps the length almost close to L. So delta L is very small to L, very small compared to L. Similarly, here, let's say the deformation is delta X. Let's say this is delta X. So we can similar to last example, we can say delta X certainly is proportional to the force applied. The higher the more you apply the force, the more is going to get deformed. Also, if you apply the force on a bigger area, that means if this is the top surface, but you apply a force on this top surface, then we know delta X will go down, which means this guy will have a greater deformation, shearing deformation, than this guy with the same force F, because you see this has a bigger area and this has a bigger area and this has a smaller area. Okay, so that holds true also. Also, delta X is proportional to the height h, which means this height, which we can see from here. This guy will deform less for the same force than this guy. So this guy is going to get deformed more than this guy. Something like this. Maybe it won't deform that much. Same as it will deform much less than the taller guy. So delta X depends on the height of the block, and all this can be combined similar to this in a form to be written as S equals F over A divided by delta X over H, and this is called the shearing stress and this is the shearing strain, and this is called the shear modulus.
and the first one was called the Young's modulus. So this is the second case. Let's talk one more case. Let's say you have a box of some volume. Well, let's say some general volume. It's a volume, not an area. Let's say it's in volume, and you apply a pressure on this volume. Let's say it's a bag full of water, and you apply pressure on the volume, and let's say it has a volume V. Then what will happen, because of this pressure P, your volume will shrink. And how much is going to shrink? Let's say it shrinks by an amount delta V. And so there's a formula that tells delta V, or in fact there's a formula that tells B equals delta P, or in fact P divided by delta V over V. And this is called the bulk's modulus. So applying pressure reduces the volume by a certain extent. And these are many different things, but they are used a lot, and so we discussed 3 of them. We'll solve at least one problem to understand what's going on.